Okay, welcome to the lecture and introduction to large deviations. Today is lecture number 6, and we are going to talk about weak large deviation principle and exponential tightness. Weak large deviation principle and exponential tightness. You know that for the large deviation principle, we need to prove the lower bound and upper bound. Let me quickly recall that if we have a family of random variables in some metric space E, a family of random variables in a metric space E, then we say that this family satisfies the large deviation principle if it satisfies two inequalities. We say that psi epsilon satisfies the large deviation principle in the metric space E with the rate function I, that is a function from that metric space to positive numbers or plus infinity. If it satisfies two inequalities, the first inequality is that for every set f that is closed in E, we have the estimate that the lim sup of when n goes to infinity, epsilon logarithm the probability that psi epsilon belongs to f is less or equal than minus infimum over f of the function I. And the second, we know that that for every so we have that for every open set in E, the lower limit, so lim inf and going to I'm sorry, no n, so here is epsilon going to 0. Epsilon goes to 0. Epsilon logarithm the probability psi epsilon belongs to G is larger or equal than minus infimum I over the open set G. And also we discussed with you that to prove the lower bound here, actually it is enough to consider only the probabilities when psi epsilon belongs to open balls. So actually, roughly speaking, you need to check only this inequality for G open balls in so for G being open balls in the metric space E. That simplifies a lot of proving that some family satisfies the large deviation principle. This idea doesn't work directly for the upper bound. So in the next example, we will show that if you know that that kind of inequality for open balls or for instance, compact sets, and later I will also explain the reason why we talk about compact sets, then actually it does not imply that you will have the upper limit for every closed set. But also we would like to have this idea that that to check up the upper bound, it is enough to check for smaller sets of for smaller class of sets. And our idea today will be the following. First of all, we will make that this assumption in our lecture weaker, and we will require only that the family has to satisfy the upper bound only for closed sets. After that, we will show that this property is equivalent to the case when you control the probabilities only on balls. And after that, we will introduce the concept of exponential tightness and show that having the upper bound only for closed sets and exponential tightness, we can immediately get the bound for closed sets. Roughly speaking, we want to split the obtaining the upper bound on two different or two separate problems. First of all, we show the upper bound for closed set. In this case, we will say that the family satisfies the weak large deviation principle. And then we want to show that the family is exponential tight. In general, this splitting is not if and only if. Later, you also will see some statement. You will see when this idea also will work in inverse direction, but we will come to that later. Now I want to start with the example where we will show that having the inequalities, for instance, on the metric space R only for intervals or even compact sets, it does not imply the upper bound for every closed set. And that example is quite easy. Is a quite simple, example 6.1. And here we consider random variables which are just constants. We take psi epsilon is equal to 1 over epsilon for epsilon larger than 0. And these are random variables in R, and set the rate function x that is equal to plus infinity for every x from R. Then for every say compact set F in R, in particular F, you can take, for instance, interval AB. So we have the following equality that lim sup epsilon goes to 0, epsilon logarithm the probability psi epsilon belongs to F. It is equal, and every compact set it is a bounded set, and psi epsilon is equal to 1 over epsilon. So therefore, you have the sequence which converges to plus infinity, and it means that starting from some small epsilon, this will not be satisfied for any bounded set F. Therefore, that probability will become equal to 0, and logarithm of 0, according to our assumption, it is minus infinity. So therefore, the limit is equal to minus infinity. And of course, it is minus infimum over f of the rate function I. Therefore, you see that for every compact set, this type of inequality is satisfied. But now you can build a very easily example for which of closed set for which that inequality is not satisfied. And this example, but for closed set, and this example is, for instance, you take F that is equal to the complete space, and you know that it is the closest set in R. You have that we have that limit going to so epsilon logarithm the probability psi epsilon now belongs to R, and it is for every epsilon, it happens with probability 1, actually for every omega, because now psi epsilon is a constant, and you have probability 1, therefore logarithm of 1, it is 0, and then this limit is equal to 0, that of course is not less or equal than minus infinity, that is minus infimum over R of the rate function I. Oh, this example shows now that the upper bound for compact sets. Or so in that case, also for balls in particular, for intervals, does not imply the upper bound for closed sets. So therefore, in general, you cannot simplify. You cannot simplify the upper bound, for instance, proving only for some smaller class of sets like compact sets just for free, as we did that for the lower bound for open sets. But still, it makes sense to start working with this inequality for compact sets first, because if, as you will see later, this will follow. I mean, the upper bound for compact sets will follow from the upper bound only for balls. And after that, we will introduce exponential tightness. And as I already said, this will imply the upper bound for all closed sets. Oh, then the definition. 6.2. We say that the family psi epsilon satisfies the weak large deviation principle in E with rate function I if we have that if so limit epsilon goes to 0, epsilon logarithm the probability psi epsilon belongs to f is less or equal than minus infimum I of x, x belongs to f for every f compact in the metric space E, and also the lower limit is equal to or can be estimated from below by also minus infimum x belongs to the strategy I of x for for every, it's better to write every G open in. And as you see, that the family, the family psi epsilon, epsilon larger than 0, that is equal to 1 over epsilon, satisfies the weak large deviation principle in E with, I'm sorry, in R with the rate function I that is equal to plus infinity, but not large deviation principle. And to distinguish large deviation principle or the previous definition and the definition which we have now, often we will say, we will call this large deviation principle, the usual one, as a full large deviation principle, not full large deviation principle. We showed that in previous example that upper bound is satisfied only for compact sets. For the lower bound for this family, it follows trivially because this infimum is equal to infinity. So therefore here you want to have the lower bound by minus infinity for this family, but it is always satisfied because the limit cannot be smaller than minus infinity. So therefore, as we wrote, this family satisfies weak large deviation principle, but not full. Also, in the literature, you can find other examples of families of large of the family of random variables that satisfy weak large deviation principle, but not full large deviation principle. Maybe here I should refer you to one of the paper of Kuznetsov, who was it seems that a PhD student with Professor Andrei Anatolyevich Dorogovtsev. And so just see, for instance, one of his work. He also has nice example. So, so it is a paper from 2015. You can find the precise link to that paper in the lecture notes, and there you, as I said, there you will find the example that interesting example for which weak large deviation principle is satisfied, but not full large deviation principle. But we will go further, and now we will prove the following proposition. 6.4. Let psi epsilon be a family of random variables in a metric space. Be a family of random variables in a metric space E, and let I be a function from E to 0 plus infinity. Then the upper bound, that upper bound here, we will just copy it. The upper bound, this one follows from the following property, that limit. You consider, let me start that differently. Let me first of all write that you consider that the same limit, but only for ball with center at point X and radius R. And then you make a radius of balls going to 0. And then you expect that the right-hand side, when you make the radius going to 0, instead of infimum, you just will have just I and 1 point. Then here we will write less or equal than minus I of x. And if this property is satisfied for all x from E, when Brx, it is the ball, it is all points from E such that the distance between x and y is less than this, the ball. And now we want to use the compactness of this set F, because here we will cover this set F by poles, and then we will find or we will select a finite subcover to obtain to show that this inequality implies that inequality. Let's do that more carefully. Proof. We fix some compact set F, I'm sorry, let F be compact set. Then let's also set alpha, it is equal to infimum I over the set F. Actually, here you see that here we want to show that inequality, therefore we denote that infimum here by alpha. And assume first that alpha is finite. If alpha is equal to plus infinity, the proof is similar, and I will leave that as some homework for you. Then, in this case, when alpha is finite, let's remark that for every x from f, we have that I of x is larger or equal than I of x that is equal to alpha. Oops, I'm sorry, something stupid written. It is infimum over f of I, and and it is equal to alpha. Actually, here we don't use that alpha is finite. We use the finiteness of alpha in the next step. Hence for any delta that is positive, we have that the limit that r goes to 0. So this assumption is given of epsilon logarithm the probability that psi epsilon belongs to the ball of radius r with the center at point x. First of all, according to our assumption, it is less than minus I of x. But this I of x, you see that I of x is larger or equal than alpha. Therefore, when you put here minus, then you need to inverse your inequality, and you will have minus here. Therefore, we can continue that estimate and write that it is less or equal than minus alpha. But now we want to work, you see that we work with limit, and somehow now we want to like remove this limit which is here. So therefore, it is not convenient for limit have that this inequality less or equal. It is better to have the inequality like strictly less. So then let me, since alpha is finite number, or and minus alpha is finite number, you can add delta. For you can write that it is strictly less than minus alpha plus delta. And now you see that limit is strictly less than some constant. And since it is so, you can always find r probably small enough such that for starting from that r, this will be also smaller than that constant, because the limit is strictly smaller than this constant. And consequently, for every x from f, you have that they exist radius which depends on x. We denote it r within this subscript x that is positive, such that the limit which is inside here is smaller than minus alpha plus delta for every r which is larger or which is smaller or equal than this rx, in particular also for exactly for rx. Oh, therefore, we show with you that for each x, I can find the radius such that the limit which I here is strictly smaller than minus alpha plus delta. And we did that for every point of the set f. Therefore, now you can consider this situation as follows. You have the set f, the compact set f, and for every point, you found a ball with positive radius for every point. Of course, it could happen that you have uncountably many balls. But if you consider all balls together, so it's complicated to like draw that for every point. But from the picture, you see that that actually this family of balls is an open cover of the set F. Note that B R X, we center at point X for all X from F is an open cover of F. What does it mean? It means that all sets are open, balls are open, and union X over F, B R X of X contain all points, contains all points from F. And now from analysis, we know that every compact set, um, that for every cover, open cover of compact set, you always can choose a finite subcover by the compactness of F. There exist points x1 and so on up to, say, xm from F, such that you have that F is a subset of union k from 1 to m, balls of radius x r x k x k, and now we can estimate the lim sup of the set F by lim sup of the union of balls. You have a lim epsilon goes to 0, epsilon logarithm probability psi epsilon belongs to F. And now using the monotonicity of probability, you have that this probability is less or equal than probability that psi epsilon belongs to the union of balls. We can write that. The probability psi epsilon belongs to union BRXK, XK. And now we can use the subadditivity of the probability that tells us that the probability of union, because psi epsilon belongs to union, it is the union of events that psi epsilon belongs to each ball. Therefore, you have the union of events, and that union and that the probability of union is less or equal than sum of probability. And then here you have the sum k from 1 to m probability psi epsilon belongs to the ball. And now you should remember the exercise which we already used a few times. We use that for two sets, but of course you can do just iteratively. You can repeat that for more than two sets, for say for m sets, for finitely many sets. And you remember when you have logarithm and here you have the sum. For instance, you have an plus a epsilon plus b epsilon. Then when you pass to the limit, you will have that limit with a epsilon and then maximum that limit with b epsilon. Then that I can rewrite as follows. It is equal, and by the way, it is exercise number 3,8 in the lecture notes. It is equal to maximum, okay, from 1 to m, lim epsilon goes to 0, epsilon logarithm the probability of psi epsilon belongs to the ball xk. But now you know that these limits are less or equal, or maybe strictly less than that. It is strictly less than minus alpha plus delta. Then we can continue. It is less. No, therefore maximum also is less than minus alpha plus delta. But this is You remember that minus that alpha it is infimum. I'm sorry, I should change the color. It is equal to minus infimum I over f plus delta. And you see the left-hand side is exactly what what is in the upper bound here, and you obtain it minus infimum plus some delta, where delta was an arbitrary number which was non-negative. Left-hand side doesn't have any delta, therefore you may you can let delta go into plus to 0 plus to 0 from the right hand side, and then you will get exactly the inequality that we want to have. It was and it was so therefore we get the inequality. And also it remains to discuss the case what is the proof for alpha is equal to plus infinity. And in this case, just you need to replace, then you need to repeat that proof, but only replace in all computation minus alpha plus delta that you saw here a few times by minus 1 over delta. And everything also will work. I leave that for you. Okay, good. Do you have any questions?
No.
Oh, oops, I did something. Katya, you will need also again, so probably like just cut off that part of where I ask about whether there are questions and so on. Okay, then if there are no questions, then let's go to that next section or next topic, that is exponential tightness. And then you will see how exponential tightness together with weak large deviation principle will imply the full large deviation principle. We have section 6.2 exponential tightness. And we just simply start from the definition. 6.6, a family of random elements psi epsilon is said to be exponentially tight X. Right, in E if for every number beta, if for every number beta that is usually is taken to be positive, there exists a compact set K set K that is subset of E such that we have that limit epsilon goes to 0, lim sub epsilon logarithm the probability of psi epsilon does not belong to K is less or equal than minus beta. In other words, you can always for every beta as large as possible, usually here you should take beta very large, you can always find the compact set such that when you consider the probability that your random variables are outside of that xi, then this probability becomes really very small. It becomes smaller than minus the delta. Of course, here the set k is depends on beta. Let me also remark that we remark that that in the case of sequence psi n, you actually should remember that we started our lectures not with a family xi epsilon, but with some sequences of random variables, and then we discussed large deviation principle for them. So also it will happen later that we will work, we will consider some sequences of random elements, and in that case, you just need to a little bit reformulate or change that lower and upper how looks limits in lower and upper bound of the definition. Therefore, the exponential tightness also will look differently. Namely, it is then we remark that in the case of sequence, the exponential tightness uh, corresponds to the statement that lim n goes to infinity, now sequence n goes to infinity. Here you have some constants that goes to 0, as in the definition of large deviation, and then logarithm the probability psi n belongs to k, does not belongs to k, is less or equal than minus beta for some a n going to 0. And then also I want to formulate some exercise which probably also gives you a little bit better feeling what the exponential tightness is. That is exercise for you, size 6.7, that says that proves that the family psi epsilon is exponentially tight if and only if and only if for any for each b that is positive, there exists a compact set k that is a subset of E, and number epsilon 0 larger than 0, such that you have that the probability psi epsilon does not belong to k. It goes to 0 faster than e to the power minus 1 over epsilon b for every epsilon from 0 to epsilon 0. Actually, this exercise, or to show that exercise, everything what you need to do, you just need to recall the definition of limit, and then just rewrite or write that what means that the limit is less than some constant, and then you immediately come to that inequality. And also similarly, when you move in the different way, you will get that upper bound which is in the definition. I also want to say that this exponential tightness somehow looks like usual tightness for a family of random variables or a family of random measures. And you can show that the exponential tightness implies the usual tightness for a countable family of random variables. But the usual tightness does not imply the exponential tightness. And you can consider that as some exercise. That exercise is formulated in lecture notes. And also I will give you some homework exercise where you can think why it is so. Um, okay, but maybe also it would be good to have some example of exponentially tight family of random variables. Since we already gave the definition, it would be nice also to see some example. And let's consider the following example. It is 6.9 in the lecture notes. And here we consider let psi is a normally distributed random variable with zero mean and covariance matrix that is identity function in RD. So in other words, psi, it is that the random vector psi1 and so on psi d where psi I normally distributed with parameter 0, 1 and independent of each other. And then we consider psi epsilon, that is square root epsilon multiplied by xi. And we already show that this family satisfies the large deviation principle. We know that xi epsilon satisfies the large deviation principle in RD with rate function I of x, that is the norm of x squared divided by 2. And now we want to show that that family is exponentially tight. And to do that, let's use the upper bound for that in the large deviation principle. So we fix some beta that is positive and take some compact set that is so as that is that the product of the intervals. Actually, we have the interval a minus so a. It is the box of dimensional d such that the infimum of the function I that over that the points is not in that box. So actually here is RD without, but we want to have the closest set. So instead of closest set, let's write minus a to the power d. You can always choose such a that this inequality is satisfied because that I it looks like the parabola, roughly speaking. So say in dimension one, so like for dimension one, your function looks like that. So therefore, when you take some beta that is here, that you can always find a. For instance, you can take here, and it is minus a, such that when you take the infimum over that set, you see that infimum will be larger than this value. And the same is for higher dimensions. And then choosing zk, let's see what happens when we consider the upper limit, the upper bound in the large from the large deviation principle. Let's write epsilon goes to 0. Epsilon logarithm the probability that psi epsilon belongs to Ka. Does not belong, I'm sorry, does not belong to Ka. That means that limit epsilon belongs to 0. Epsilon logarithm the probability that psi epsilon belongs to the set Rd minus Ka. Actually, the complement of Ka. But the complement here is an open set, but we want to use the upper bound. And upper bound in large deviation principle is given for closed set. So therefore, we can extend this set a little bit, just including the boundary. And replace it by Rd minus the open bound, the open cube. And then a dim. And this set here is closed. Therefore, by the large deviation principle, for this family of random variables, we can estimate that the lim sup by minus infimum over that set Rd minus a comma a of I. But we choose this I so large such that it is the infimum is larger or equal than minus infimum is smaller or equal than minus p. That implies that psi epsilon is exponentially tight. Well, and immediately from this example, you see that if you already know that the family of random variables satisfies the large deviation principle, and actually the rate function also satisfies some kind of good properties, something like you already saw here, then you have the exponential tightness for free. Later also we will have the statement that the full large deviation principle implies exponential tightness, but it is for a sequence of random variables. Now I want to combine two concepts or two definitions that we introduced today and show that they implies that the upper bound is the large deviation principle. Namely, next statement will be about the following, that if your family is exponentially tight and satisfies weak large deviation principle, then it satisfies also full large deviation principle. It is the proposition 611 is the following. If a family psi epsilon is exponentially tight and satisfies the weak large deviation principle in E with rate function I, then it satisfies the full large deviation principle. Moreover, if I is lower semi-continuous, we already discussed the lower semi-continuity of rate functions and uniqueness of rate functions last lecture. Then I is good. It means that the level sets of I are compact sets. And now we want to prove that proposition. And here the idea of proof is that weak large deviation principle gives you a good control of lim sup on for compact sets, and exponential tightness, it gives you a good control outside the compact sets. So therefore, if you start from some closed set, then you just want to choose some compact sets for which you have a good control of probabilities outside that compact sets. This compact set is from the definition of exponential tightness. And then you want to split your F on two sets. One set, it is F intersect with compact set that is also compact, and also everything else. Let me realize that idea. So we take F subset of E closed, and also let beta and K be as in definition in definition of exponential tightness. So it means that that K is compact, and you have that lim epsilon logarithm, the probability epsilon to 0, psi epsilon does not belong to K, is less or equal than minus beta. And then for that F, K, and beta, we can estimate the probability that psi epsilon belongs to F is equal the probability that psi epsilon belongs to F intersect with K, or psi epsilon belongs to F to K minus F. Oops, I'm sorry, belongs to you have F, then you will have F intersect with K complement, right? And then using that the fact that that probability is additive, that two sets are disjoint, you will have the probability psi epsilon belongs to F intersect with K, plus the probability that psi epsilon belongs to F intersect with K complement. But now, actually, you see that here you have the probability where what is written here, that is equivalent that psi epsilon belongs to K complement. And so therefore, I mean, you can forget about this set F. And when you remove this set F, you become something larger because this event is larger. Then you can, then we estimate the following probability limit. Epsilon goes to 0, epsilon logarithm, the probability psi epsilon belongs to F is less or equal, upper limit, epsilon logarithm, and then you also have the probability that psi epsilon belongs to F intersect with K, plus the probability that psi epsilon belongs to K complement. And again, you have that upper limit for epsilon logarithm, and here is the sum. And again, using the same exercise as we use today for balls, we can estimate, or that limit, it is equal to limit epsilon larger going to 0, epsilon logarithm the probability psi epsilon belongs to f intersect with k. Maximum, this we use for maximum. Actually, when we write a, b, it means maximum a comma b. Then maximum with lim epsilon goes to 0, epsilon logarithm the probability that psi epsilon either belongs to k complement or that is equivalent does not belong to k. And you see that by the large deviation, weak large deviation principle, you can control that limit because this set is compact. And this, you can control that limit by exponential tightness. Then we obtain minus infimum. Infimum, and here the set f intersect k of I maximum minus beta. And we note that that infimum, of course, it is smaller. It is larger or equal. No, wait a moment. I want to say that this infimum, right, it is larger or equal than infimum of I over the larger set F. Because infimum always becomes smaller when you make set larger, but now you have minus. So therefore you will have the equality in that direction and you will need to put the minus. Then you have less or equal that minus infimum over the set Fi maximum minus beta. And now beta was any positive number. The left-hand side is independent of beta, and you have beta only here. Everything what you can do, you can make. Now let beta goes to plus infinity. Then you have that this goes to minus infinity. And then maximum between something, some number, and something that goes to minus infinity will be exactly that. So therefore this will goes to minus infinity. Oh, minus infimum over f. And this is the way how we can get the upper bound for every closed set. Because we can split that on compact set and something that is outside of compact set that we can nicely control by exponential tightness. Everything what we have to prove here is that we have to show that if the function, if lower semi-continuous, rate function is lower semi-continuous, then it is a good rate function. We will show. That I is good. It means that for every beta, every alpha that is larger or equal than 0, when we consider that the set of all x such that I of x is less or equal than alpha, then is compact. But we recall that the level set is closed since I is lower semi-continuous. Last time we discussed that every lower semi-continuous function satisfies the property that each level set of this function is closed set, and that is if and only if. Therefore, now we assume that I is lower semi-continuous. You also know that having large deviation principle, you can always replace rate function by lower semi-continuous rate function. That also was discussed last time. And now everything what we have to show, we want to show that this function is not only closed set, but also it is a compact set. For that, let's take let's take K from K compact from the definition of exponential tightness with beta that is equal to alpha plus 1. Now, once again, the exponential tightness is here, and then we just take beta that is equal to that beta is equal to alpha plus 1, and for that there is the compact set K for which that inequality is satisfied, and then we take that K here. And then let's see that, and let's show that actually the level set of the function I is a subset of this compact set K. Let's note that minus infimum, we use that the fact that psi epsilon satisfies large deviation principle. In particular, for every open set, you have that the limit infimum epsilon goes to 0, epsilon logarithm the probability that psi epsilon belongs to K complement. Note that this set is open as a complement of closed set, is larger or equal than minus infimum x belongs to K epsilon of I of x. That is less or equal than minus beta according to the choice of that compact set K. It is minus alpha minus 1, and that is strictly smaller than minus alpha. So this, we came to the inequality that when you take infimum over the set K, I'm sorry, it's K complement of I, then is that infimum is larger than minus alpha. So in particular, this implies that for every x from K epsilon from K complement, you have that I of x must be larger than minus alpha because infimum is strictly larger than minus alpha. But what does it mean? It means that inequality here, it means that x cannot belong to this set, because if it belongs to the level set alpha, then I has to be less or equal than alpha. So in particular, it implies that for every x from K epsilon, you have that x does not belong, or you can say belongs, to the level set I less or equal than alpha but complement. Either you say does not belong to set or belongs to the complement. So I'm sorry again, complement. So in particular, it's implies that K complement is a subset of the level set complement. But if you have like this one subset is one set is subset of another set, and then when you take complement, then you need to invert your that sign that it belongs. So in particular, it means that I belongs to, and since I less or equal than alpha is closed, it is compact as a subset of a compact set. This implies that the rate function is good. Oh, therefore, here you see that the exponential tightness gives us the goodness of rate function. So therefore, if the rate function is not good, so therefore you should not expect that your family is exponentially tight, because then it would contradict the statement that we proved. But we have the better situation when we work with a sequence of random elements, and it will be my last statement today. that we will discuss. It is the proposition, it is the following proposition. Six, 12. Let E be and now we assume that it is a complete and separable metric space. Now assume that the family psi epsilon, psi n, we have the family of random variables, the countable family satisfies the full large deviation principle with a good rate function I, with a good rate function I. You must assume here that the function is good, because it is not good, then you should not expect that you have exponential tightness, according to the previous proposition. Then it is exponentially tight. It is exponential. And to show the exponential tightness, everything what we need to do, we need to build a compact set for every beta. We need to build a compact set on which we can nicely control the probability that psi n does not belong to that compact set. And to do that, we will use like a family of balls, and we will build so using the intersection and union balls, we will build a totally bounded set. And you know that in complete separable metric space, the closure of totally bounded set is compact set. And actually, it is the tool that we are going to use here. So, okay, proof. First of all, let's note that the space E is separable. And since it is separable, well, we can cover E by some countable family of open balls of radius 1 over k for any or for each k from n. We may cover E by some open balls. And then you know that bk1, actually now for us it doesn't matter where the center is and what precisely the radius is. No, radius, it makes sense for us, of radius 1 over k. Okay, so actually we have the set E, and we covered it by balls of radius 1 over k, by a countable family of Z balls. And then we put U, k, n. It is a union of Z balls. So here M, I'm sorry. N is already reserved. B, K, J. So therefore you take the union, and of course the union will converge to the complete space E. And now our goal is that that we fix beta that is positive, that is from the definition of exponential tightness, which we want to check, and k from n and show that there exist mk, so for each k, there exist mk larger or equal than 1, such that the probability, such that for every n larger or equal than 1, you have that the probability psi n does not belongs to uk mk is small, is smaller than epsilon, less or equal than epsilon minus beta k divided by a. Wait a moment, it is typo, I'm sorry, it should be. It's less or equal than, once again, what you do here, you have the space, it is a space E, and then you cover that by balls of radius 1 over k. You have countably number of balls, and then you want to show that you can choose a finite number of z balls such that the probability that your psi epsilon is outside of that union of balls actually goes to zero like exponentially faster. So this, you remember that the an goes to zero, and that is in the definition of large deviation principle, and you want to show that inequality. So actually you want to show that for every n and also for every k. And to do that, let's do the following. We first remark that that the level set of level beta k, so it is that beta k that is here, that we denote that is actually the level set I of s less or equal than beta k, but here it's not enough for us beta k, exactly, let's take plus 1. And this set is compact. Compact because I is good. And you know that for good rate function, each level set is good. And now we know that since this boss, which we considered of radius 1 over k, and so on, is also open cover, not only the complete space, but also each subset, and in particular also this level set, is an open cover L beta k. They exist a finite subcover cover beta b k g1 and so on, e k g for instance L of L beta k. Well, of course you can choose these indices ordered for convenience. And then trivially, if you take the union of all balls up to this index, then it will contain the union of z balls, but that is subcover of this set. So therefore, the union of all balls up to that index will contain that as a subset. We have that then trivially L beta k is a subset of u k g l. And now we can use that the upper bound by the upper bound for the large deviation principle, we get, or we conclude that that lim n goes to infinity of an logarithm the probability that psi n belongs to that union of both, but we want to consider the complement does not belongs. We want to control that probability is less or equal. By the way, this set here is that set here is closed because you have finite union of balls that is open set. And you take the complement that is a closed set, and therefore you can use the upper bound here, and it is less or equal than minus infimum I over so the complement of that union of balls up to the index GL. But you see that this set here is larger than that one. Therefore, the union, so therefore for the complement here, you have that inclusion for complement. And now you compute the infimum over the smaller set here. So therefore, when you replace the infimum by and you will I mean over that larger set, it will become smaller, but then also you have minus that will gives you larger. Then you have less or equal than minus infimum I of L beta k complement. And what means that this that x that taken infimum over that set. So let's note that for x that belongs to L beta k complement, or it does not belong to that set, it means that it does not satisfy this inequality. Therefore, you have that for such an x, you have that I of x is larger than beta k plus 1. That gives you that it is that infimum, therefore also infimum is larger or equal than that set, and then you can estimate this less or equal minus beta k minus 1. And so you have that this set is larger or equal than that constant. Of course, if you forget about this one, about this minus 1, then you can replace this inequality less or equal by strictly less. Maybe it makes sense also to write that it is strictly less minus beta k. Therefore, the limit is strictly less than that constant. And according to the definition of limit, you can find a number n such that starting from that number, this one also will be less than minus beta k. So therefore, you have that this implies that there exists a number n larger or equal than 1 such that for every n less or equal than n, you have that an logarithm, the probability psi n belongs to ukjl complement is less or equal than beta k, and of course this is equivalent. That is equivalent to the fact that the probability psi epsilon, oh sorry again, psi n belongs to ukjl. This small l depends on k, of course. That is less or equal than e minus beta k divided by an. And that is for every n larger or equal than n. But you want to have that for every n. So, and then to make this for every n, next, so let's note that next, using the fact that the probability that psi n belongs to uk comma m. So this again uk m, it is the union of both m first balls, and you consider it does not belongs. And you remember that this set it increases. This converge to the set of the complete space E. And then the probability, it is a continuous function. It is the continuous from below and continuous from above. Therefore, and since this set increases to the complete space, and here you compute the probability that xi n does not belong. So therefore, this event, it decreases to the empty set, and then the probability must converge to the probability of empty set that is 0. That is equal to 0 as m goes to infinity. Therefore, in this, so having this in mind, we can find mk larger or equal than jl such that this probability psi n does not belongs to u k m k is less or equal is small enough, and it is less or equal than the probability psi n does not belongs to k jn that is less or equal e beta k a n, and that is for every n larger or equal than. Once again, so here you see that by the computation that was done before via large deviation principle, you can choose the n so large such that for every n you have this inequality which we wanted to have, but also there remains small n, so like n is equal to 1, 2, up to capital N minus 1. And for this n, what you can do, you can say, okay, when we take the union of sets, like many sets, then this probability goes to 0. And therefore, for fixed k and fixed n, you can choose that m so large, then this probability also is smaller than that number. And then you take your index mk, first of all, larger than gl here, and also large enough that this probability is smaller than that number for all n from 1 to the capital N. And then, of course, you have also this inequality for n large enough, and then you can control that probability by by that exponent for every n. And now let's note that now we sum the previous inequality over k. And we consider so the probability that psi n does not belong to the intersection u k n m k. What it is? It is a probability that psi n belongs to the complement. But you know that the complement of intersection, it is a union of complements. You have k, m, and complement, and then you use a sigma additivity. It is less or equal than sum k from n from 1 to infinity, the probability that psi n belongs to u k m k. I'm sorry, here should be k complement. But you see that each probability here here we estimated by such an exponent. So therefore, you can continue the estimation and say that it is less or equal than k from 1 to infinity, and that it is e to the power minus beta k divided by a. That is, it is the geometric series, and when you compute it carefully, you will get minus beta divided by n divided by 1 minus e to the power minus beta an. Oh, and therefore, now take k be the closure of the set. It is the intersection of union of both of radius 1 over k, finite number of balls, okay, which is compact, since the set intersection of balls is totally bounded set, is totally bounded, totally bounded. What means totally bounded? It means that for every small number or every radius, you can find a finite number of balls of that radius or smaller than cover that set. And it is indeed so, because this set here is obtained as follows. You just take mk balls, you union them, and then you take intersection over balls that have smaller and smaller and smaller radius. So therefore, for every radius which you like, you can find k large enough such that 1 over k is even smaller, is smaller than that radius. And of course, like balls that are here, they will cover this set because it is the intersection. So therefore, you also can consider the limit n goes to infinity of an logarithm the probability psi n belongs to k. Does not belongs or belongs to k complement or does not belong to k. First of all, you want to we say that that closure of this set is larger. Therefore, complement of closure of this set it is smaller. Then you can write the estimate here by the limit an logarithm the probability that psi n belongs to that intersection of that balls. And this is and that is equal to limit n goes to infinity an logarithm, and here you have e to the power minus beta an divided by 1 minus e minus beta an. And when you compute that limit, you will see that limit is, I think it is exactly equal to minus beta. And that finish our proof. And here I want to say that the proof of this statement is much, much simpler if you assume that your space is finite dimensional. Because for finite dimensional space, you know that every closed ball is a compact set. So therefore here, in the case of finite dimensional space E, your proof will be much simpler because you don't need to play with this intersection union of balls. There you just can build only one ball for which your limit, that limit is small enough that will gives you immediately the proof, because the closed ball will be a compact set. But if you are in complete separable metric space, then you know that balls are not compact sets, and then you just need to play with balls, doing something to build the compact set for which you can control that limit. It was actually what we did here. Okay, my time is already over, and I want to summarize what we learned today and how we will use that material later. And to summarize that, let me come back to the definition of large deviations. And in the definition of large deviations, you have two types of inequality. You have the upper bound and you have the lower bound. I'm sorry, it is not definition. Here is the definition. You have the lower bound for open set and upper bound for closed set. And long time ago, we proved that to get this inequality, it is enough to take your G balls and control these limits only for balls. And then we observed that actually the balls, it's not enough to obtain the upper bound. And therefore, our idea was to split the problem on two problems. The first problem is that you want to get the control of upper bound for balls that gives you a control for compact sets. And in this case, we say that the family satisfies the weak large deviation principle. And then we wanted to extend that property from compact sets to closed sets. And that it is possible to do when you have the exponential tightness, when you can nicely control that type of probability outside of some compact sets. So therefore, we introduce the notion of not understand what is going on. We introduced the notion of exponential tightness and prove that exponential tightness together with weak large deviation principle gives you full large deviation principle. Next time, we will prove the large deviation principle for Brownian motion. And then we will apply our strategy. We will first show that the Brownian motion satisfies the weak large deviation principle, and then we will show the exponential tightness, which will guarantee the full large deviation principle for the Brownian motion. And it is everything for today. Thank you so much for your attention, and see you next time.